Hello friends and welcome to a lecture on operation research. Today we will learn about maximum flow in a network. I am Professor Arvind Prasad. Let's look at a problem to get you into the context of what we are discussing now. We have a network. The network is on your screen. So you have node 1 to node 7 and in between you have a lot of nodes. Now in between the node you have directed arcs. So from node 1 to node 2 the flow can only happen from 1 to 2. Okay. So in all these nodes you have flow from the previous nodes. Okay. Now, what is the maximum flow if these numbers which are near the arcs, that is from arc number 1 to 2, you have 6. Arc number 2 to 5, you have 4. If these numbers represent flow, what is the maximum flow you can have from node number 1 to node number 7? Node number 1 is your source and node number 7 is your sink. Okay, so what is the maximum flow you can have? Supposing I introduce a flow to the left of node number 1. Okay. How much maximum flow I can have through this network so that that flow can come out through node number 7 to its right. So the maximum flow, of course, is find the maximum flow. The problem is find the maximum flow that can enter 1 and leave 7. Now, what are the constraints? Now, each arc has a flow restriction. As we can go back and have a look, it has a flow restriction. From arc 2 to 5, you have a flow restriction of 4. From arc 5 to 7, you have a flow restriction of, once again, 4. And other flow restrictions are very obvious. And you cannot have any reverse flow. Remember one thing, you cannot have a flow from 1 to, you can have a flow from 1 to 2, but you cannot have a flow from 2 to 1. Okay, so what should be the maximum flow? What can be the value of the maximum flow? That is, if we can find something about this, then we can think about, where should we, what should be the optimal value? Okay, then we can work towards getting that optimal value. So for that, you have the max flow min cut theorem. Now, what is the max flow min cut theorem for a network? So for a network with a single source and a sink, the maximum feasible flow is the minimum cut value over all the cuts. I'll explain you in the next slide. What does it mean? Now, what is a cut? Okay, a cut is if you take a network and you draw a line through all the arcs. So a cut is, it partitions the nodes into two disjoint sets. Okay, one set will contain all the nodes which have the nodes plus the source, and one set will have all the nodes on the other side, which will be those nodes plus the sink. So into two disjoint sets where you have one set of nodes and source, one set of nodes and sink, and it's a cut in between. So that's known as a cut. Okay, now for the network that we have, let us look at what is a cut and what is not a cut. Well, if you take this particular line, which cuts this entire network into two, where you have node 1, 2, 3, 4 and source on one side, and 5, 6, 7 and sink on the other side. Now this is a proper cut. This is not a cut. Why? Because if you do this cut, remember one thing, you do not have the source on one side because you have the source still attached to 4, and you also clearly do not have the sink and the other nodes on one side because you have arc 1, 4 still connecting in between them. So this is not a cut. A cut should be such that if you cut along that part, the network should be into two disjoint sets. That is very important. Okay, now let's see what is the minimum cut for a network. You have to do it. It comes through trial and error, as you might like to call it. But you have to cut various arcs through your network and see where do you get the minimum value, which cut gives you the minimum value. Now the minimum value that you have is 9. If you make this first cut So what you have here is the arcs going in here are 6, 4 and 1. So the flow in the cut is 6 plus 4 plus 1, that is 11. If I make the cut here, let us say the cut is along here. So these arcs have a flow value of 4 plus 1, 5, 5 plus 3, 8 and 8 plus 4, 12. Okay, so this is when I make a cut here, the flow in the cut is 12. Now, if I make a cut here, the flow in the cut is 13. But this particular cut, as you can see here, it has a minimum value of 9. So this is your minimum cut. So this is the maximum flow that can go through the network. So at least what it gives you is, when you do this exercise, it gives you a perspective of what is the optimal value of the maximum flow that can be in the network. Now remember one thing, you may not always be right while doing it. But if you do this exercise, you at least know where is the minimum value likely to be. You might end up, at the end of the problem getting a value lower than that. But if you're getting a value higher than that, maybe you have not solved the problem correctly. Okay. Now let's go into what is residual. Residual is the flow that can be assigned to an arc. So let's take an example. Now, this is the current network that we had. This is shown on your left. It is small, okay, but pay attention to it. You have node 2, 5 here, where the flow, maximum flow in the node can be 4. Okay, so I have copied it down here. So you have 2, 5. So this is your arc 2, 5, and the maximum flow that you can have through this arc is 4. Now, let us say, supposing I assign a value of flow through this arc. Okay, so let me assign a value of flow 3. Okay, now if you go to see the residual flow, that is the flow remaining which can be further assigned in this arc, is 1. Okay, and the flow already assigned is 3. Okay, initially if you go to see the residual flow from 2 to 5, that is arc 2 to 5, is 4. But if we assign a flow of 3, the residual flow is going to be 1. Why? Because you have already assigned 3 and 3 is written on the other side. So 3 is the flow that I can put in the reverse direction. Now this helps sometimes in solving the network. That is, you convert this into an undirected network. You see, you replace this arrow with an undirected network. But the undirected network has a sense now in numbers. In numbers, what it says, the residual flow from 2 to 5 is 1, but the residual flow from 5 to 2 is 3. That is, in reverse, a flow of 3 can be sent. So it does give a sense to the flow. And it helps in solving the network at a later end. Okay. Now, starting with the residual network. Now, this is our starting residual network. Remember one thing, what I have done here now, all the arrows have been replaced with lines. Okay. Why? Because now you have put numbers to put a sense into the direction. So 6 is the maximum flow that you can assign from 1 to 2. That is arc 1, 2, arc 1, 3, maximum 4, arc 1, 4, maximum 1, so on, so forth, from source to the sink. Now, what is an augmenting path? Augmenting path is a path you draw from the source to the sink in the network. Okay, right? A path is nothing but a collection of arcs. Remember one thing, a path is nothing but it's a collection of arcs. Now, this collection of arcs is such that all the arcs in this collection have positive residuals. Positive means not 0, greater than 0. Remember this. In this particular network problem that we take here, that is the maximal flow for, problem, the positive is always greater than 0. Okay. Now we take our residual network and we start off with it. Our starting residual network was already shown to you here. So we take this up and we draw our first augmenting path. Now the first augmenting path that I draw is here from 1 to 2, 2 to 5 and 5 to 7. So it is shown as a yellow line here. Okay. So this is my augmenting path here. And what is the capacity of this augmenting path? The capacity of this augmenting path is the minimum capacity of the arcs or the collection of arcs that is in the augmenting path. So the arcs that you have here are 1, 2, 2, 5 and 5, 7. Now what is the minimum value of the residual here? It's 4. It's 4 here too, but if you have a tie here, you take the minimal. Okay, you take any one of them. So it's 4 here. So this is the capacity of the augmenting path now. Okay, now remember one thing, the capacity of the augmenting path 1, 2, 5, 7 is 4. It is not 6 because 6 is the higher value. The maximal flow logically also which can go from 1, 2, 5, 7 is 4 because 4 is the minimal flow that occurs here. Now, of course, the residual network now it modifies to, we write the numbers here as you can see here. Now 6, we reduce 4 from here and we write 2. So 2 is the residual of arc 1, 2 in direction 1, 2 and in direction 2, 1 the residual is 4. That is a reverse flow of 4 can still be sent from 2 to 1. Okay. Now if you go from 2 to 5 it is 0, 4, 0, 4 because we have assigned a flow of 4 here. So the residual capacity now that remains in arc 2, 5 and 5, 7 is 0. Now we draw another augmenting path. So the other augmenting path that we can draw is 1, 3, 4, 6 and 7. Right? Before we go ahead, now in the source, the arrow that is entering the source, we write a value of 4 here and in the sink also we write a value of 4 here. This is merely to show that now a flow of 4 can flow through this network. So we have assigned a flow of 4 in this network. Now afterwards we take the second augmenting path 1, 3, 4, 6, 7. Now the minimal flow here is if you go to see it's 3. Okay, so we can assign a flow of 3 to this and if I assign a flow of 3 to this is the residual network you will get where the arc 1, 3 will now be residual will be 1. In the arc 3, 4 the residual will be 0. In the arc 4, 6 the residual is again going to be 1. And in the arc 6, 7 the residual is now going to be 6 because we had assigned C3. So 9 minus 3 makes it 6. Now we assign one more residual network. Okay, we draw one more augmenting path to this. The augmenting path this time is 1, 3, 6 and 7. Okay, so if you take 1, 3, 6 and 7, the minimum that you can assign here is, now you see why we write these numbers. The minimum that you can assign here is 1. See, because 3 can be assigned here, 6 can be assigned here, but the minimal is 1 now. Okay, now if we assign 1 to this, there we are. Now from arc 1 to 3 is 0. Arc 3 to 6 is 2. The residual value that remains now is 2. And 6 to 7, the residual value now remains is 1. It is 1 less from the previous number. Now finally, we put this as one more augmenting path, that is 1, 4, 6 and 7. Okay, so again here if you go to see, the minimal is at two places. 1 to 4 you have a minimal residual value of 1 and 4 to 6 also you have a minimal residual value of 1. So you assign 1 and you get ahead and you make the changes. So this is the final network you get, and each time when you assign flows you update the numbers here at the source and the sink arrows. So the maximum value that you have put in the flow now is 9. Let me show it how we progressed. The last I had shown is from here. So from 4, last we had done was 4. Then I assigned a value of 3. So it was 7. Then afterwards I assigned a value of 1. It was 8. Then the augmenting path 1. And finally you have 9. So 9 is the maximum. Now if you go and have a look at the network, there is no way you can assign further flow in this network. Why? Because if you go and assign a flow from 1 to 2 here, if you draw an augmenting path from 1 to 2 here, the subsequent path has a capacity of 0. You cannot get ahead. Now 1 to 3 already has exhausted its capacity, because 1 to 3 the residual flow is 0. 1 to 4 also the residual flow is 0. So we have now assigned the maximum flow capacity to the network, and that is 9. And initially also, when we had made cuts, that is in the max cut, what you say as min cut. Okay, max value min cut. Oh, it was not max value min cut. Let me get the name. It was, yes, what is a cut? It was max flow. Sorry, max flow min cut theorem. Max flow min cut theorem. So in the max flow min cut theorem, also we had got a value of 9. Okay. So there we are. We have a value of 9, and this is the network. Finally, this was our final one, and this is the final network that you have. That is from 1 to 2, it is 4. 2 to 5, it is 4. And also, this is not the only optimal solution that you have. This is the optimal value. But you can have a network of this kind also. So just have a look from what is this is the first one that we had arrived, and this is the second one. In the second one, what we have done is the flow from 3 to 4 is 1. It is not 3 as it was, as we had done. So this could be one alternative solution. It is 1. And the rest of the flow is 3 to 6 is 3, because 3 is what you could assign maximum from 3 to 4. So we assign maximum there and we go. And then of course 4 to 6 we assign a value of 2, and we come back to the same numbers, that is 9. Okay. So that is all about how to solve a maximal flow problem in a network. Okay. And well, this is the Ford's algorithm. Remember one thing, I have not shown you something new. This is the Ford's algorithm. Okay. Now, I have not used the word explicitly because I was more interested in showing you the algorithm. But if someone says use the Ford's algorithm to solve it out, well, this is actually the Ford's algorithm itself. So fine, we come to the end of our lecture. If you like my lecture, do share and subscribe it. As you can see here, I do not use a very strict tone in delivering lectures, because that's not my style of teaching actually. And if you do like my work, do share it with your friends, and do comment on areas where you want videos, and I'll put them. Operation research is one of the areas which I have a lot of interest. There are other areas, and you can obviously go to my YouTube channel and have a look at them. But operation research is now the current area in which I'm making videos. So do like and subscribe my channel, and do share my videos. Goodbye friends. Have a great day and have a great time.